Okay, well, welcome to the third lecture, chapter 9, more reactions of alcohols. Set up again. Here we're starting in sections 9.12 and 9.13. Okay, we essentially established that we can activate alcohols by acidic conditions. Okay, we can activate them towards substitution or elimination. Now, we want to activate alcohols in different ways. We sort of introduced this with POCl3. We could activate it with phosphorus. Now we're going to use things like sulfur and more phosphorus. Sulfur and phosphorus basically are the two biggies. Okay, so 9.12 is conversion of alcohols to alkyl halides with SOCl2 and PBr3. We're going to change. We're not going to use PBr3. We're going to show how we can convert to a chloride, a bromide, or an iodide, or something called a tosylate. Okay, so all of these are creating good leaving groups in situ. Okay, we say in situ means in the reaction mixture. Tosylates you can actually isolate, but the rest of them are sort of in situ. So we're going to treat 9.12 and 9.13 together. 9.13 is about tosylate. So let's look at a big picture scheme. We've got an alcohol. We want to make a chloride. Okay, alcohol to alkyl chloride, we said we could use HCl. Okay, we can still do that. Or we can use SOCl2 and pyridine. We'll show all of these. We want to make a bromide. We can use HBr. Or we can use what's called NBS and triphenylphosphine. We want to make an iodide. We can use HI or I2 and triphenylphosphine. Or lastly, if we want to make a really nice leaving group, probably one of the best leaving groups, O-tosyl, then we can use tosyl chloride and pyridine. We already know what tosyl is. It's tosyl OH is para-toluene sulfonic acid. So this is tosyl chloride. Okay, we'll show all these things. So these are four reactions that are very similar in mechanism to what we've been going over. So let's go one at a time. Alcohol, SOCl2, pyridine. Again, I'm going to give you structures, but SOCl2, I give you a Lewis structure. You got to be able to draw that out. OH to Cl. How's this work? Put our lone pairs on oxygen. Draw out SOCl2. Okay, there's a resonance structure. This looks a lot like DMSO. You can draw a resonance structure in which there's a plus on the sulfur and a minus on the oxygen. I'm going to leave it like this. We're going to treat it like SN2. Complicated, but we're going to treat it like SN2. SN2-like. Now we've activated, or we're beginning to activate, our alcohol. Let's charge that Cl minus that left. Again, the Cl minus is not a base, not a good base. Pyridine, however, is a decent amine base. You can deprotonate. It's going to give a byproduct. Pyridinium, we call it. Cl minus. It's a plus charge on the nitrogen. That's our byproduct. What do we get? You can draw the byproduct over here if you want. We showed an arrow like that oftentimes, but the Cl minus of the byproduct is now going to attack And what's going on here is you're going to lose SO to gas and a Cl minus. It's going to give product. You formed a chlorine carbon bond. We lost SO2 gas, and that's a driving force. There's entropic reasons why that's favorable. Losing gases is going to help drive a reaction. And then now we get this byproduct that's done reacting, plus Cl minus this ammonium salt. You'll see this a lot. Ammonium, pyridinium, ammonium salt, ammonium chloride salt. Okay, so that's the first mechanism, SOCl2. Let's look at the bromination. Again, we could have used HBr. This is probably a better way. Here we got a more complicated mechanism. We have to activate this is triphenylphosphine. We've got to activate our bromine in a sense. This is called NBS, N-bromosuccinimide. This is a good leaving group. This phosphorus is going to attack the bromine, break the the bromine nitrogen bond, and give phosphorus with a plus charge on it. What's the associated negative charge? It is this guy. Succinate is what it's called, N-bromosuccinimide. So the succinate is a good leaving group. It's a resonance stabilized nitrogen anion. Okay, so it can leave under these conditions, and now we can activate oxygen. So all this is sort of activation. The oxygen attacks. We're beginning to activate our phenols. We can talk about that in class. It's just the aromatics. Sorry, there's no charge there. Plus charge there. And now we have a much more acidic proton. We can use that to deprotonate. And now we are almost set up. We've got a byproduct. It's protonated nitrogen. And now the bromine can leave from phosphorus. Three phenols, that's a phosphorus. That's got a plus charge. And now, same idea. All of this was activation of the oxygen. And the driving force here is the formation of an oxygen-phosphorus double bond. Bromine is going to attack here. Good leaving group. Oxygen-phosphorus. You get product, and you get what's called triphenylphosphine oxide. You get a phosphorus-oxygen double bond. That's a strong bond. Okay, so this whole thing is a good leaving group. Okay, it's a lot of mechanism, I know that, and you just got to write these out over and over. Okay. The next one is an iodide. It's OH, I2, triphenylphosphine. Same idea. I2 can be activated by triphenylphosphine. This can attack an iodine. Heteroatom bonds are generally weak, so we can do this. We can break them apart. That's going to give this intermediate. If you calculate the formal charge on phosphorus, it's just like nitrogen, 4 bonds, it's got a plus charge. The difference being that phosphorus can house a 5th bond. Again, we rationalize this by p orbitals, okay? Probably not a sufficient explanation. Inorganic chemists would argue with me, but we kind of talk about d orbitals in phosphorus and sulfur. There's just an orbital that's accessible on phosphorus. And here we're doing very similar things that we just did with bromine. Sorry, there's also pyridine in here. Pyridine is going to be our base. I forgot because you can actually get away with doing this without pyridine, but we want pyridine is important. Same idea as in SOCl2, pyridine will come in, deprotonate, okay, we're going to get a byproduct here. What is it? It's the protonated pyridine, I minus. And then this iodine leaves. Again, after all that work now, we are set up for this whole group to leave. Okay, so in fact, we have a lot more than 4 leaving groups. We have chlorine, bromine, iodine, and water. Those are the 4 we mentioned. And then we have other ones that are generated in the reaction from POCl3, SOCl2, NBS, the one we just did, and then this one. Okay, this is the same leaving group. So what happens? You have I minus comes in here and attacks, forcing out triphenylphosphine oxide. You can abbreviate it that way if you want. Again, strong phosphorus oxygen double bond helps with that driving force. All right. Now let's talk about tosyl chloride. Tosyl chloride, same idea, but we're going to create an even better leaving group. Tosyl chloride is an abbreviation. Again, I would give you the structure. Here's pyridine. Interestingly, that oxygen is staying put. We're activating this first to create a leaving group, and then we can do SN2 and things like that, just like a bromide. Okay, so let's show this reaction. Tosyl chloride is the same as para-toluene sulfonic acid, but instead of an OH, it's got a chloride, so it's a very different reagent. We have lone pairs on this oxygen. There's no proton to deprotonate. This can happen. Again, we're going to treat this as SN2 for now. Okay, there's more to it, but we're not there yet. We're going to treat this like SN2. So now we are activating the alcohol in a different way. Make an oxygen-sulfur bond. Like so. And now what happens? Pyridine can come in and pick up that proton, push the electrons. That gives you the O-tosyl. Okay, that's our product. Tosyl is this whole group. And what do we lose? We lose a protonated nitrogen, pyridinium chloride. Okay, so that's the formation of a tosyl mechanism. Okay. Okay, so this is different mechanistically because this alcohol stays put. So let's illustrate this. Stereochemical implications. We went through the mechanisms of each. Now let's show, this is a 6-membered ring. Let's show this with all 4 of those reactions again and talk about what's going on stereochemically. SOCl2, pyridine. These are all SN2 reactions with the exception of the tosyl. Okay? SN2 means we're going to get inversion. So let's assume this is a meso compound. Okay, so but essentially a single enantiomer, meaning the key point here is we're getting inversion at this stereocenter. We're going from cis, let's call it cis instead of single enantiomer because it is a meso compound. So the cis goes to the trans. And the NBS, pyridine, goes to the trans. I2, triphenylphosphine, pyridine, goes to the trans. All 3 of these undergo SN2, SN2, SN2. Okay. Now the tosyl, chloride pyridine, gives only retention. Sorry, that's only retention because we haven't broken the carbon. Mechanistically, this makes sense. It's not retention and inversion because we're not going through a carbocation. We're sort of activating the OH into an O-tosyl. Okay, it's a tosylate, and we haven't broken any carbon-oxygen bond here. All we've done is formed an oxygen-sulfur bond. So this just never changes. Never changed. Okay, so this is retention. Okay, all the rest of them are inversion because they underwent SN2. The CO bond was never broken. Let's look at some more stereochemistry in a retro synthesis kind of way. Okay. Let's say we want to make a CN, this stereochemistry, single enantiomer. Okay. I just go back to this slide really quickly. Sorry. I misspoke. Okay. This is not a meso. Okay. The 1,4 would be a meso, and a 1,3 with 2 methyls would be a meso, or 2 alcohols. Okay. So I just misspoke. That's not a meso compound. So it's cis, and it could be a single enantiomer. Okay. So let's say we want to make this cyano compound as a single enantiomer. Okay, there's lots of ways we can do this. Okay, let's start off with the chapter 7 way. You could use sodium cyanide and start with the bromide. Okay, this bromide single enantiomer, you could do SN2. Inversion. Let's do let's ask the question, if we could make this from an alcohol, how would we do this? Okay, let's say an alcohol that is an inverted alcohol, okay, the opposite configuration. We can't go directly. You can't add sodium cyanide to an alcohol, okay? You can't actually add HCN, like an acid, kind of like we do with HBr, so you can't do that. But what you could do is use a tosylate and sodium cyanide. Think of a tosyl as a even better leaving group. Really, this is actually the best leaving group we've seen. Why? Because it's resonance stabilized. Doubly. Okay. This is actually probably a better leaving group than even Br or I minus or Cl minus or water for sure. Okay. So if we did sodium cyanide, that would give SN2. Again, you got to think backwards. We're talking about this right here plus sodium cyanide going in the forward direction. That's what we mean here. So now we can easily make the tosylate from the alcohol. We just showed that, tosyl chloride and pyridine. Okay, that stereochemistry is going to work out because you don't break the carbon-oxygen bond there, and so you get retention. So you go from here to the tosylate to the cyano. Okay, that's the forward sense. One more thing. Let's say you had the alcohol. All you had was this alcohol, right? Then you can make the bromide. Say you needed that alcohol and you wanted to go to the cyano, but it's retention. So now you got to do essentially double inversion. Okay, so this bromide can be made from the alcohol by what? NBS triphenylphosphine, but not HBr. Why? HBr would form a carbocation and it would undergo SN1 and give racemization, but NBS is going to go alcohol to this bromide and then to that. Okay, so these are complicated things. Keep working on them. Again, let's do a couple more examples, or let me give you a couple more examples for take home. Let's start with this cis substituted single enantiomer. And we want to do tosyl chloride, pyridine. Ask what we're making there, and then we're going to treat that with sodium ethoxide. Okay, I just broke it up for space. It's all one thing. Sodium ethoxide, let's put it down there. Sodium ethoxide, what do you get? Two-step process. Tosyl chloride pyridine. Sodium ethoxide is going to add to that. And we're talking about substitution products here. Okay. Tosyl chloride, or sorry, the tosylate is a very good leaving group. Okay. Let's show something else. Potassium tert butoxide. What do we get here? Okay, remember what potassium tert butoxide is, and then what a tosylate is. So predict those products, and we'll have one more lecture on ethers and epoxides when we come back for our last one.